Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine you're just, standing outside on a clear night. You're looking up at the sky. And suddenly, this brilliant shooting star blazes right across the darkness.
It's a beautiful sight.
Right. It's beautiful, and it's this completely unpredictable, spontaneous surprise.
Unless it isn't a surprise at all.
Exactly. Okay, let's unpack this, because what if humanity knew exactly when and where that rock would arrive? Like, down to the actual minute and the square meter on the ground.
That is the reality we're stepping into. I'm excited to be here to talk about this because the mission of our conversation today is to really explore the Vera Rubin Observatory, or the VRO.
And its legacy survey of space and time, right? The LSST.
Yes, exactly. This is a monumental technological achievement that is about to permanently change our relationship with the sky. We're transforming Earth from a blind target into a fully aware planet.
Which is wild to think about. I mean, consider for a second how vulnerable Earth actually is. We're just spitting through a cosmic shooting gallery.
We really are. And historically, we've had almost zero visibility on the smaller debris crossing our path.
Right. And catching even those tiny, completely harmless space rocks, it completely alters our planetary defense strategy. The sheer scale of the universe is just mind-boggling, and the fact that we can track a single rock out there is incredible.
The scientific implications of predicting these meteorites are profound. It's a level of analytical precision that, frankly, borders on science fiction, but it's happening right now.
So before we talk about the rocks themselves actually falling to Earth, we need to understand the machine that's watching them. We're moving from this concept of a blind Earth to the activation of humanity's newest, most powerful eye.
Waking up the giant, essentially.
Waking up the giant. So let's talk about the VRO itself. It's located down in Cerro Pachon in Chile, right?
Right, high up in the Chilean Andes. The atmospheric conditions there are pristine for astronomy.
And it recently had this explosive entry into the astronomy world. I mean, in just one single night in February of 2026, the VRO sent out an astonishing 800,000 alerts.
Yeah, that number is almost difficult to internalize.
800,000.
Yeah.
In one night.
Yeah.
I mean, my phone gets overwhelmed if I get like 30 group chat texts. How does an astronomical community even process that?
Well, to understand that, you have to look at the instrument itself. The VRO is taking what they call cosmic treasure chest images. It's equipped with a 3.2 gigapixel camera.
Wait, 3.2 gigapixels?
Yes. It takes these incredibly deep, wide-field images of huge patches of the sky.
That is just a massive amount of data.
It is. But a static image doesn't tell you what's dangerous or what's changing. So the software pipeline instantly takes that new image and overlays it onto a pristine, high-resolution template image.
Like a baseline image of that exact same patch of sky.
Yeah, exactly. A template built from years of previous observations. It uses a technique called difference imaging.
So it's basically the ultimate spot the difference puzzle. You take the archival photo, lay tonight's photo on top of it, and just subtract everything that matches.
That is the exact mathematical process. Literal pixel subtraction. The distant stars, the galaxies, they all perfectly align and cancel each other out to zero.
Making them invisible in the data.
Right. And whatever is left behind, whatever doesn't perfectly align, glows in the data. That leftover pixel is the alert.
So it means something has either changed in brightness or it physically moves.
Exactly. But dealing with 800,000 of those alerts in a few hours is a logistical nightmare.
I would think so. I mean, it's like having a security camera that doesn't just record a whole city, but instantly texts you every single time a leaf blows across any sidewalk. The signal-to-noise ratio must be insane.
It is. The sky is littered with junk right now. Low Earth orbit satellites, space debris. A satellite streaking across the frame triggers an alert.
So how do you filter that out? You can't have human beings checking 800,000 text messages.
No, you can't. The data goes through these massive, automated, machine learning-driven filter systems called brokers.
Okay, brokers.
Yeah. These algorithms are trained to instantly recognize the geometric signature of, say, a satellite streak, or the predictable pulsing of a variable star. They strip away the known noise in real time.
Okay, so the brokers are like a massive sieve. You dump the raw alerts in the top, and the true anomalies fall out the bottom.
Exactly. And what's fascinating here is the VRO's primary mandate. It wasn't actually built primarily for asteroid hunting.
Wait, really? With all this tracking tech?
No, its primary and famous targets are mapping dark energy, studying supernovae, and cataloging active galactic nuclei, foundational physics.
So the really big, deep space, Nobel Prize-winning stuff.
Right. But to map dark energy, you need sweeping, rapid, panoramic shots of the visible sky every few nights, which inadvertently makes the VRO the greatest local surveillance camera ever built.
It's like a accidental local surveillance.
Exactly. While it was built for deep space foundational physics, its bycatch is arguably more important to our daily survival.
Bycatch. I love that term. Like a fishing net pulling in millions of asteroids and tens of thousands of near-Earth objects, or NEOs.
Precisely. And that sheer volume of data leads directly to a very specific, incredibly rare type of discovery.
Right. Objects that are on a direct collision course with us. The imminent impactors.
Yes. And we need to define that term clearly. An imminent impactor is a natural body discovered in space before it hits Earth.
The before being the operative word there.
Exactly. And to understand how the VRO handles these, we have to look at the work of Ian Chow and his team at the University of Washington.
At the Dirac Institute, right?
Yes, the Dirac Institute. They didn't just guess how good the VRO would be. They ran a rigorous simulation using a survey simulator called SORCHA.
SORCHA, what exactly did that simulation do?
They programmed SORCHA to virtually replicate the VRO's exact schedule, its downtime for weather, the sensitivity of its sensors, a complete digital twin.
Oh, wow. So they simulated the machine itself, not just the rocks.
Right. And then they injected reality into it. They mapped 343 known historical fireballs from NASA's Center for Near-Earth Object Studies database.
These were past fireballs spanning from 1994 to 2026, correct?
Yes. Specifically, they were looking at 1-meter-sized objects. They ran the orbital mechanics backward and asked the simulation, if the VRO had been running, would its digital twin have caught them?
Okay, so they're testing a new machine's capabilities against known historical data to prove its future efficacy. That makes sense. But let me push back on something here.
Sure.
Why do we care about a 1-meter rock? I mean, a rock the size of a washing machine just burns up in the atmosphere anyway, right? Why dedicate world-class supercomputers to simulate harmless rocks?
It's a great question because those small rocks are the key to understanding the big picture. They provide a ground truth compositional map for the entire NEO population.
Ground truth, meaning we can actually test our theories against physical evidence.
Exactly. When we look at a massive 500-meter asteroid, it's just a dot of light. We have to analyze its spectrum to guess if it's solid iron or a loose rubble pile.
Which would totally change how you try to deflect it if it was heading for us.
Completely. Now, an imminent impactor gives us a unique value. We can track the object through 3 phases.
Okay, what are the phases?
First, as an asteroid in space, where we get that telescopic light data. Second, as a meteor entering the atmosphere, where we see how it burns and breaks apart.
Which tells us its structural strength.
Right. And third, as a meteorite on the ground. Because we tracked it so precisely, we can calculate where it landed, pick it up, and take it to a lab.
So you're closing the loop. You match the physical chemistry of the rock on the lab table with the light data the telescope saw days earlier.
Exactly. Every time we do this with a harmless 1-meter rock, our predictive models for the massive, dangerous asteroids become exponentially more precise.
That is brilliant. It's like using the small rocks as a Rosetta Stone for the big ones.
Precisely.
Yeah.
And knowing how the VRO spots these leads us to the most critical metric of all.
When it spots them.
Yes. Time is the ultimate currency in planetary defense.
So how much time are we buying here? Because the VRO is expected to find, 1 to 2 meter-sized or larger NEOs each year?
Yes, which effectively doubles the current global detection rate.
Doubling the rate is great, but the warning window is what really matters. I have the numbers here. It says the simulation showed a median discovery time of 1.57 days before impact.
Right, about 38 hours.
And a median time of first observation of 3.06 days. So anywhere from a day and a half to 3 days of warning.
Which sounds short until you look at the historical context. Before this, the previous record for the longest warning time we ever had was back in 2016.
And what was that record?
A mere 21 hours.
21 hours, that's nothing.
It's barely enough time to verify the math and notify the government. VRO simulations show some objects being found weeks in advance.
Here's where it gets really interesting to me. I mean, think about the psychological and logistical difference between 21 hours and 1.57 days, or even weeks.
It's the difference between panic and procedure.
Exactly. It's like hurricane tracking. A day and a half isn't a lot of time to move a mountain, but it's plenty of time to board up the windows. Or, in astronomy's case, to point every telescope on Earth at the sky.
That's a perfect analogy. What happens globally when that 38-hour clock starts ticking is a massive, coordinated pivot.
Every observatory just drops what they're doing.
Right. This doubling of warning time fundamentally changes astrometry from a reactive science where we just watch it fall to a proactive one. We swarm the target with radar, infrared, optical telescopes.
Because the more eyes you have on it, the more precise the trajectory gets.
But time is only half the equation. You can have all the time in the world, but it's useless if your telescopes are pointed at the wrong half of the sky.
The geometry problem.
The hemisphere blind spot. Historically, as we discussed, only 11 imminent impactors have been detected prior to hitting Earth.
Only 11 in all of human history.
Yes, and there is a massive bias in those detections. Almost all capable astronomical facilities are located in the northern hemisphere.
That is a terrifying blind spot.
It is. Take the specific example of the impactor designated 2024 XA1.
Okay, what happened with that one?
In December 2024, it was detected just 10 hours before impact by the Kitt Peak Observatory in Arizona.
10 hours. Unbelievable.
And it ended up striking the remote Sakha Republic in Russia. It was a northern hemisphere telescope catching a rock on a northern hemisphere trajectory at the absolute last minute.
So imagine the Earth spinning. We're constantly exposing this unmonitored southern flank to the cosmos. It's like driving a car where all the mirrors only show you the right side of the road.
You're completely blind to traffic merging from the left.
Exactly. You've got zero visibility until something hits you. That's how humanity has been tracking asteroids until now.
And this is where the VRO's location in Chile becomes critical. It provides a powerful southern hemisphere counterpart, finally balancing our global vision.
Curing the blind spot.
Yes. If we connect this to the bigger picture, global astronomical infrastructure is a shared human responsibility. International cooperation and geographic distribution of these observatories are mandatory for our survival.
Because the asteroids don't care about borders. They'll hit the north, the south, the equator.
Exactly. The VRO gives us that global visibility.
So we have the extra time and we have the dual hemisphere visibility. Now, what exactly do scientists do in those crucial hours before the rock arrives? The so what phase?
Well, that advance warning allows for highly detailed study. We don't just calculate where it's going, we figure out what it is.
Right. The pre-impact observation.
We measure its albedo, which is how reflective its surface is. We study its surface roughness, its taxonomy.
And its rotation period, right. Seeing how fast it's tumbling through space.
Exactly. And if it's close enough, we can bounce radar off it. The longer we observe it, the longer our observational arc becomes.
And longer observational arcs equal highly precise trajectory tracking.
Very precise. Let me give you an example. The 2023 CX1 event.
Oh, I've heard of this one.
The global network tracked it so well that scientists predicted its impact trajectory to within an astonishing 18 meters.
18 meters. So what does this all mean? I mean, 18 meters is predicting a cosmic sniper shot from millions of miles away to land within the space of a tennis court. Through the atmosphere, no less.
With all the chaotic fluid dynamics of the atmosphere, yes, it's an incredible feat. And that precision is what makes recovery possible.
Right, going out and picking up the pieces. But wait, since most of the Earth is covered in ocean, isn't meteorite recovery usually impossible? Like if it lands in the middle of the Pacific, it's just gone.
Normally, yes. An ocean impact is a total loss for meteoriticists. However, the extra warning time from the VRO makes something incredible possible. Airborne dust sampling.
Airborne dust sampling. Okay, break this down for me because this sounds like science fiction.
When an asteroid hits the upper atmosphere, it vaporizes. It creates a massive fireball, but as that vapor cools, it condenses into microscopic dust suspended high in the stratosphere.
Like a lingering smoke trail.
Exactly. And because we have 38 hours of warning and an 18-meter error margin on the trajectory, we know exactly where that smoke trail will be.
Oh, wow. So you scramble an aircraft?
Yes. Specialized aircraft, like modified WB-57 bombers, fly directly through the lingering smoke of that vaporized asteroid over the ocean.
Wait, they just fly a bomber through the plasma dust cloud?
They do. The planes have sticky aerogel filters on their wings. They trap the airborne dust of the fireball before it ever settles to the ground.
That is absolutely mind-blowing. You bypass the ocean entirely and catch the rock while it's still floating in the sky.
Exactly. This brings physical pieces of the cosmos directly into a lab. It validates all the distant math and physics we rely on. We get our ground truth.
It's an incredible scientific triumph. But getting 1-meter rocks in cosmic dust is just the warm-up, right?
Yeah.
The real reason this entire system exists is the ultimate goal: planetary defense.
Yes. We want to protect humanity from the rocks that don't just burn up.
Right. Because catching a 1-meter rock is cool, but a 140-meter rock will flatten the state.
Exactly. The 1 to 2 meter size detections per year act as a baseline. They are a training ground for the global network.
It's a fire drill.
It is, because for the rarer, much larger, and far more dangerous impactors, the VRO's sensitivity will extend that warning time from days to weeks.
Weeks of warning for a major asteroid. That changes everything.
It does. It allows for coordinated, worldwide observing campaigns. We can determine the exact orbit and, most importantly, mount actual planetary defense initiatives.
Okay, so what does a planetary defense initiative actually look like with 3 weeks of warning? Because you can't build and launch a deflection rocket in 21 days.
No, you can't deflect it with that short of a window.
Right.
But you can mobilize geopolitical and scientific resources. You can initiate massive civil defense and evacuation protocols.
Moving millions of people out of the impact zone.
Exactly. If we know a city-killer asteroid is going to hit a specific coastline in 3 weeks, we can empty that coastline. This is where the simulation of the harmless 1-meter rocks pays off.
By perfectly rehearsing the exact communication and governance protocols needed for the big one.
Precisely. The data pipeline is the same, only the payload is different.
It's just so ironic, isn't it? We built this massive telescope, carved off the top of a mountain in the desert, to look at the absolute edge of the universe, to look at dark energy and billions of years into the past. And its most practical use might literally be saving our own backyards from a falling rock.
It is a beautiful irony of foundational science. But this raises an important question. How will humanity govern and coordinate this information when a real threat is detected weeks out?
That's the real test, isn't it? The telescope just gives us the math. It's up to human beings to actually figure out the geopolitics of an evacuation without causing global panic.
The machine works perfectly. The human element is the variable.
Wow. It's an incredible journey we've mapped out here. We went from a single observatory high in the mountains of Chile, processing 800,000 difference imaging alerts a single night.
Through the broker algorithms filtering out the noise.
Right. To a global network that is capable of catching incoming fireballs days or even weeks before they strike, curing our southern hemisphere blind spot, and giving us the power to fly bombers through cosmic smoke.
It is a total paradigm shift in our situational awareness.
It really is. And for you listening, it really changes how you think about your place in this newly monitored solar system. The sky above us is no longer this unknown, chaotic frontier.
It's an actively mapped, highly surveilled neighborhood.
Exactly. Which leaves me with this sort of provocative thought to ponder. As our technology improves and the sky becomes entirely mathematically predictable, we kind of lose something, don't we?
The mystery of it.
Yeah. We lose the spontaneous magic of a surprise shooting star. That serendipity is going to be replaced by a push notification telling you exactly where and when to look.
We trade the romance of the unknown for the security of the known.
Beautifully put. But in exchange, we gain the ultimate power, the power to survive the cosmos. When we finally know exactly what the universe is throwing at us, how will that change our perception of our place in it?
We evolve from passive targets to active participants.
Exactly. We are no longer just along for the ride in the dark. We are finally learning how to read the maps and maybe, just maybe, learning how to steer the ship. Next time you stand outside in the dark, remember that there are massive digital eyes staring right back, making sure the road ahead is clear. Keep asking the big questions, keep looking up, and we'll see you next time.
Yeah.